Yeah. Last week I was in Vienna, but as you can see, I caught a cold. Okay, so I have a sore throat, and yeah, I still have to teach. So so my voice may be a little bit low. Okay, if you cannot hear it very clearly, I mean, let me know. I will try my best. Okay, or you can sit closer. I wear the mask already, so it shouldn't, cause any problem for you. Okay. How? Okay. Yeah, I just heard like some students don't know like when the midterm is. Okay, it is the next week. Okay， 就下个礼拜期中考哦，下个礼拜期中考。请大家不要记得，不要到时候 ，OK， I will not be here next week. Next week. Actually, it's a worst timing for me to have a cold because the next week I'll be in China, and the week after next I'll be in Malaysia, okay, for a conference. So, but I probably have to go see a doctor like today, okay, to get some medicine, okay, just to make sure I survive, for my trip in China. But anyway, when I'm not here, okay, next week there will be a midterm for you guys, okay, and here will proctor the midterm, okay, and as for the week after next, okay, as I told you already, like I will have a makeup class. Again on Saturday. It should be, let me see, 25th. We will have a class on 25th, the morning of 25th. Okay. So it's again like a long weekend, the 25th. Okay, so let's do it like the previous way. Okay, if it's long weekend, I will let you go. Okay, so see that your family, but can we do like a class online? Okay, is that okay? And then the week after next, like as I told you, I will not be. I'll be in Malaysia. Okay, so I will after today. I will see you again. Okay, face to face in November. Okay, November. Okay. So I will ask the TA to send out this notification, okay, to you guys, at least like to remind you, like the midterm next week. Okay, it's not like I announced it today. We announced this midterm date like a long time ago, but this is just a reminder. Okay, and the second thing is the makeup class is on the October 25th. Okay, in the morning from 9 to around 12 o'clock. Okay. 就是你们帮忙，什么东西？好像没有发给你。Oh, okay. Okay. I'm sorry. I will. Give me like 1 second. 1 minute. midterm, right? So whatever we covered today, okay, will be the range, okay, from the beginning of the class, okay, to whatever we cover today. Okay, this will be covered by the midterm. Okay, but because we only have like 2 classes today, so I think like we will only cover a little bit. We will not be able to cover the whole chapter, okay, of the linear transformation. Okay. So this chapter has 3 sections. We will be lucky if we can finish section 2, okay, today. Okay. So first, we need to know what is linear transformation. Okay. Here's the definition of the linear transformation. Okay. V and W are vector spaces. Okay. We already know the definition of vector spaces, right? So the function L from B to W is called a linear transformation if L AU plus BV equal to ALU plus DLV for any scalar AB and the vectors UB and V. Okay? So this is a very, very simple definition. Okay? And the linear transformation may not look like what you have in mind. Like, I mean, like some format, okay, may be slightly different than what you think. But anyway, let's start with like a simple example. Say the linear transformation from Lxy, okay, is mapped to a single, you can say it's a vector of one element, or you can say it's a scalar. Okay, so from Lxy to x. Okay, so this is obviously like your V and W. V has a 2-dimensional, right? It has x and y, right? And W has only 1 dimension, so it has only 1 element, right? So we now need to see like if this L, this mapping is a linear transformation, or just we check with the definition of linear transformation. L A U1 U2 plus B B1 B2. Okay, according to the from here to here, it's well, because B is a vector space, so we have that. Okay, and according to the L definition, okay, it's going to be this term. Okay, and we can write this one, okay, back to like this. It doesn't change the fact. So, as a result, okay, even it looks like a strange example, but it is indeed a linear transformation. Okay. And then, okay, here's so the previous example is like you can consider that example as a dimensionality reduction, because like you map a vector of 2 dimensions into a vector of 1 dimension, right? So this mapping reduces the dimension. Okay. The second one, okay. So Lx map is mapped to x and 2x. This one is obviously reversed. Okay, original is a 1 dimension, so it's basically a scalar. We map a scalar into a vector shape, okay, vector format. And this one, same thing. Okay, you can just plug in AU plus BV, okay, and it will give you LAU plus BV, and then it's according to the definition, AU plus BB, 2AU plus 2BB. Okay? And this one, obviously, can be treated as this one. Okay? So, because this one equal to this one, according to the definition, it is a linear transformation. Okay? So the next question is Lx mapped to x plus 1, a linear transformation. The first example, map from a vector of 2 dimension into 1 dimension. The second example, map from a vector of 1 dimension into 2 dimension. And the quiz basically is what should I say? Like it's a shift, right? That's just weight now, today. That's just a weight. But is the shift operation linear transformation? You plug in the definition. So L, okay, AU plus BB. Okay, so it's going to be L, AU plus BB. So according to the definition, this is going to be AU plus BB plus 1, right? Okay, because this is sure X, right? Which is X right there. But how about the other is A, L, U plus B, L, B. If you look at this, each of these, okay, give you U plus 1. The first one give you U plus 1 times A. The second give you B plus 1 times B. So it's going to be A times U plus 1 plus B times B plus 1. So it's going to be AU plus BB plus A plus B. So this is obviously, not a linear transformation because the top one and the bottom one are different. Okay, are different. But you get the idea. So shifting is not a linear transformation. Okay. We will see how we can make a shifting a linear transformation later. Okay. Okay. So another example. Lxy is equal to cosine, negative sine, cosine theta, okay, xy, or put it another way, it's this one. Okay, so can you show that this is a linear transformation? So it's actually a rotation. Okay, this is actually rotation. Like you have a vector x and y. Okay, in like in the space. Okay, like a 2D space. You want to rotate that vector with z. Okay, so this is what happened. Okay, this is what happened. You can check out like if it's correct. Okay. So we need to see L A U1 plus B B1 D2. Okay. And AL U1 plus BL U1 D2. You see, like if these two are the same. Okay, these two are the same. So the beginning, the inside can be combined. So it's going to be L AU1 plus BU1 AU2 plus BD2. And this is your x, this is your y. Okay, probably expand. Okay, I'm too lazy to do that. And the other one, the first one is like basically U1 sine then minus U2 sine then. Okay, and then you have U1 sine then plus U2 cosine then times A, okay, plus D times going to division U1 down. Okay, U1. And then you come, put them together. Okay, it's very straightforward. So you can verify. Okay, and then you will find out that these two are the same. These two. This one and this one. Will be the same. So the rotation is a linear transformation. So we are starting to see something more interesting. Okay. So next example. Okay. Prove that differential operation is a linear transformation in the vector space C1 A. So the rotation can be considered like geometric, but the C1 AB cannot, right? The C1 AB cannot. What is C1 AB? By the way, you guys still remember? You guys still remember what C1 AB is? Or put it another way, CNAB. It means like a function after n differentiation, it is continuous in the range A to B, right? So C1 AB means like a function after it is differentiated one time, it is continuous in the range A to B. Okay, so show is L A U plus B equal to A L U plus B L E, right? In this particular example, your U and B are functions. Okay, they are functions. Okay, they are functions that are continuous. Okay, after one-time differentiation, they are continuous in the range of A. So L, we can write it A F plus B C. Okay. And this L, what is L by the way? L is differential operation. L is differential operation. So you try to differentiate AF plus BC. What you are going to get is AF prime plus BC prime, right? And then your A L F plus B L C is going to be well A times F prime plus D times C prime. Okay, and obviously from like a you know what you learn from like a algebra, they are the same, right? They are the same. And we can do that because F and G, okay, because F and G are differentiable. Without F, G are in C1. Okay. Because of that, we can do that. We can do this and make sure that we are the same. And then, okay, a quiz. Okay, now let's prove that if L from D to W is a linear transformation, then L0 must be 0. Okay. Of course, the first 0, the 0 inside the parentheses is in the B, the space, vector space B. And the 0 outside here, okay, is in the space W, vector space W. They may have different dimension. Okay, they may have different dimension. But it's okay. It's okay. Conceptually, this must be true if L is a linear transformation. So how do we show that? Basically, it's just that because we know that linear transformation L AU plus DB has to be ALU plus BLB, right? This is all we know. So in order to show L0 must be mapped to 0. Okay. The only thing you need to do is to make U and B to be the same. And A to be 1, B to be -1. So in other words, what you are doing is L. So V minus B. Okay. It's going to be LV minus LV. I mean, this one must be in the dimension, in the vector space W. And this one is, right? And 0 in the parentheses is in the vector space. So now, once we define the linear transformation, we are in a position to talk about the kernel and the range. So what is kernel? What is range? Okay. If you have a linear transformation L from V to W, then kernel L is like whatever vector. The set of vectors in V such that we map the V through this linear transformation. They will be mapped into 0.